Hi everybody, I hope this video finds you well. In today's video, we're going to be introducing a really important concept called the sampling distribution. And this concept, the sampling distribution, really sort of bridges the gap from what we've been doing most recently with probability to sort of what we're going to be doing for the remainder of our class, which is inferential statistics through hypothesis testing. And the sort of big idea here is that you guys have now learned a lot about how to calculate different probabilities, and now we're ready to use that knowledge of how to calculate probabilities to make decisions with statistical data. But to do that, we need to know how to put those sort of probabilities that we studied to work when we actually have samples of data. In other words, we need to know what to expect when we're taking samples of data. And the name would imply that the sampling distribution does exactly that. So the sampling distribution is a relatively sort of big topic, and it's got a sort of pretty lengthy definition, and it's going to take a while for us just to understand even what a sampling distribution actually is. So we'll jump right into that definition. We'll talk about a really important theorem that sort of tells us what we can expect about the sampling distribution based on the population that we're working with. And then we'll look at one example of sort of building a sampling distribution from scratch. We'll do all of that in this video, and as we'll sort of see at the end, building a sampling distribution from scratch is a tremendous amount of work, even in really small scale cases. And that'll sort of tell us that in the future, we'll want to avoid that, and we'll actually just sort of use some mathematical mechanisms to know what's going to happen without actually building the sampling distribution at all. But we are going to do one example in this video where we actually build a sampling distribution so you guys really understand what this concept is. So let's start off, though, before we get to any of that, with our definition. So what is the sampling distribution? Well, we'll give this definition right here. The sampling distribution of the sample mean of samples of size n. So all of this here, right, that entire thing is what we're actually defining here. The sampling distribution of the sample mean of samples of size n is the collection of every average of every possible sample of size n drawn from a population with replacement. And that with replacement means that the same individual can be chosen more than once. So that with replacement means that once you pick somebody for your sample, you put them back in the population and you could pick them again. So the sampling distribution is very complex. What it is you first, from your population, have to take every possible sample of a particular size. So you might have to say you want to build the sampling distribution of samples of size 10. So you need to take every possible group of 10 individuals from your population. Then for every one of those samples, you have to calculate the average of the individuals that end up in that sample. Once you've calculated all those averages of all the possible samples, all those averages make up what we call the sampling distribution of the sample mean of samples of size n. Now, a couple important notes about this. First one, that name is already pretty wordy, and it turns out that we don't really need to always say of the sample mean. So this note says that there are sampling distributions for every possible statistic. So we could talk about the sampling distribution of the sample median of samples of size n, or of the sample standard deviation of samples of size n, so on and so forth. So there's sampling distributions in theory for every possible statistic, but we're not going to use those. For our class, we will exclusively use the sampling distribution of the sample mean. So a lot of times as we go forward, and you'll often hear me say, we'll just say the sampling distribution of samples of size n. So we'll sort of omit that of the sample mean, because the only statistic we're going to be interested in here is that sample mean. The other sort of note that I want to make here, just something to keep in the back of your mind as we go further with this, what the sampling distribution really is useful for is it tells us how the average of a group behaves. That's what it's really about. It's not about how individuals are distributed. A sampling distribution is not about individuals from our population. It's about the average of groups. So that's going to be a really important thing when we get deeper into sort of working on problems, because whenever you see an average of a group, that's going to be your sort of key phrasing to realize that you want to work with this sampling distribution thing. Okay, so To recap, the sampling distribution is a pretty crazy idea. What we're doing is we're starting with some population, which already might be really huge, and we're thinking of every possible group of a particular size, and then every average of all those groups. As you can imagine, it would be really difficult if the population was large to actually think of every possible sample. If you think that, you take a population that's relatively small, maybe a population that has 1,000 or 10,000 people in it, if you do the samples of, say, size 30, that means you have to figure out every possible group of 30 individuals selected from those 1,000 or those 10,000 and then calculate all those averages. In practice, that's not feasible. So luckily, we have a very important sort of theorem in statistics that tells us what we can expect about this sampling distribution based on the population. So let's go ahead and talk about that theorem. So this is what's called the central limit theorem. And we're going to often quote the central limit theorem, so we're just going to abbreviate it as the CLT. So if you ever see like in the notes or, as I'm talking, I just mentioned CLT, that just means the central limit theorem. So let's talk about what the central limit theorem really means. Well, what the central limit theorem says is suppose we have some population that has a mean mu. Remember, mu is our standard notation for when we're talking about the mean of a population, and standard deviation sigma, because again, we're talking about the standard deviation of a population. So we have a population and we know its mean and its standard deviation. Then the sampling distribution of samples of size n will have the following three properties. So these are three things we know automatically about the sampling distribution based on what we're told about the population. So this first one says that the mean of the sampling distribution of samples of size n, which you often write as mu with an x bar, and we'll just zoom in a little bit, so hopefully you guys can see that there, right? That's a mu with an x bar as the subscript. Anytime you see the x bar as a subscript, that means you're talking about the sampling distribution. So the mean of the sampling distribution of samples of size n is the same as the mean of the population. In other words, mathematically, mu x bar is equal to mu. Okay, now we could just take that on faith and say, okay, sure, I believe it, but let's think about why that makes sense. What this is basically saying is that the average of all the averages, so if you divide people up into groups and you take the average of every group, well, the average of all those averages is the same as if you just averaged people individually. And that should make sense, right? It shouldn't change the average if you take people individually, or you put them in groups of 5, or you put them in groups of 50. The average will remain the average. And that's all that this is actually saying here. All right, the second fact is a bit more interesting. The second fact says that the standard deviation of the sampling distribution of samples of size n will be smaller than the population standard deviation. And not only does it tell us that it's smaller, it actually tells us how to calculate it. It says that the standard deviation of the sampling distribution, notice I'm using that notation sigma with the x bar as the subscript, is equal to the original population standard deviation divided by the square root of n. So this tells us that the amount of deviation in samples is less than the amount of deviation in the population. And that should make sense, right? Basically, this is something you guys have probably heard before, that groups show less deviation or less variation than individuals. To think about that, just take as a sort of little thought experiment, imagine a room full of people, right? Maybe like a classroom, right? In that classroom, there might be all different sorts of people in terms of height. There might be some really tall people, some really short people, etc., right? Now, if you imagine that maybe the tallest person in the room is, 6'2", and the shortest person in the room is like 4'10" or something. So there's a lot of deviation. There's people from all the way at 4'10" all the way up to 6'2". Now imagine you start dividing people up into groups. Well, maybe take 3 or 4 people at a time. Well, that 6'2" person, the person who's really tall, they're going to be in a group with some people who aren't as tall as them. There might be in the group with some people who are 5 feet or 5'5" or something like that. And the average of that group is going to be a bit higher, but it won't be that high because the overall height, the average height of that group, is going to be sort of mixed between the really tall person and the more normal people. Same thing with the shorter person, right? That 4 for 10 person is very short in comparison to everybody as an individual, but if I put people into groups of 3 or 4 or 5, that really short person is going to be mixed with people of other heights, and as a group, they're not going to be as extreme. So in other words, all that's trying to do is justify that it makes sense that groups show less variation than individuals. And this fact actually tells us how much less variation. It's the original standard deviation divided by the square root of the sample size. Notice that also means that this will get smaller and smaller the larger n is. So the larger the groups are, the less the variation. That's what this second fact is really telling us. All right. The third and final fact, right, it sort of makes sense what it's going to talk about. This first one talked about the mean, which we know is a measure of center. The second one talked about the standard deviation, which is a measure of variation or spread. So the third and final fact tells us about the other thing we often want to study, which is the shape. So this third fact, which is in a lot of ways the most important, says that the shape of the sampling distribution of samples of size n will be more normal than the population. So in other words, the sampling distribution will be more normal looking than the population. In other words, more bell-shaped. Now, what does more normal mean? Well, we break it down into two separate cases. If the original population is already normally distributed, so you have a normally distributed population, then the sampling distribution will also be normally distributed for any sample size. So you've got a population that's normally distributed. You take samples of size 3, and the sampling distribution will be normal. You've got a population that's already normal, and you take samples of size 100, the sampling distribution will be normal. In other words, if the population starts as normal, then the sampling distribution will also be normal. More interestingly is this one. This one says that if the original population is not normally distributed, remember, we're very cautious around things that are not normally distributed because we don't have much that allows us to work with those, right? That sort of z-score and that table A that we've been discussing throughout our entire class, those don't apply when things are not normally distributed. But this fact says that if the original population is not normally distributed, the sampling distribution will be approximately normal as long as the sample is size 30 or more. And this is really crucial. This is saying that even if your population is horribly left skewed or right skewed or some shape we've never even talked about, the sampling distribution will be a nice normal shape as long as we take our samples as size 30 or more. And this is going to be something we use a tremendous amount. So it's a really, really important part of this. And we'll go ahead and we'll actually just star this guy because this is going to be really important. Okay, so in later videos, we're going to do a lot of computational examples using this central limit theorem on all three parts of it. But for now, what I'd like to do is actually do a very small scale example of building one of these sampling distributions, just so you guys can really see what this concept means. Now, this next example, we're going to work through it, and hopefully it should be interesting in understanding what the sampling distribution is and what these three elements of the central limit theorem really say. But I do want to caution you guys, this is more just so that you can see what the sampling distribution looks like. It is not something we're going to do a lot in practice because, again, building a sampling distribution from scratch in a real-life population is just completely unnecessary and often impossible. So this is something just to sort of get a thought experiment going to think about this. So let's go ahead and look at that example. Okay, so for this example, we're going to construct a sampling distribution from scratch. So to start off with, we're going to have a population that is absolutely tiny. It only has 5 individuals. Remember, populations often have an unknown number of individuals, usually in the hundreds of thousands or millions or something like that. But because we want to be able to do this by hand, we're going to take a very, very sort of small population with only 5 individuals. And each of them have a value for some quantitative variable, and these values are right there. So one of the individuals is a 0, the other is a 4, an 8, a 12, and a 20. So these 5 numbers represent the 5 individuals in our population. What we're going to do with this is we're going to first begin by calculating the mean and standard deviation of this population, which will be very easy. We'll just use our calculator to do so. We'll also draw a split stem plot for this population. That's not really going to look very nice because there's only 5 data points, but we'll go ahead and do it anyway. Then we're going to use the central limit theorem, the first 2 parts of it that we just discussed, to predict the mean and standard deviation of the sampling distribution of samples of size 2. Then we will actually go ahead and build the sampling distribution of samples of size 2. So we'll take a look at every possible sample of size 2 from this population, calculate the average of every one of those samples, and then look at what that distribution looks like. Then we will calculate the mean and standard deviation of the sampling distribution that we built in D. What we'll do once we've calculated this is compare it to our predictions, and we will see that the central limit theorem told us what we calculate directly, which tells us in the future we can skip this and just use the central limit theorem. And then finally, we'll draw a stem plot for the sampling distribution to actually see that third element. Hopefully it will look more normal. So we've got a lot to do. Let's go ahead and take a look at that. So we'll actually go ahead and calculate it and work through these pieces on the next page. So there's our population just for reference. The first thing we want to do is we just want to calculate the mean and standard deviation. So we can just go ahead and put our data into L1 as we normally do, and then do 1 var stat, just like we used to. And let's just write down our mean. We will use the mu notation because we're assuming this is a population. You should get 8.8, and we'll go ahead and put our standard deviation as well. You should get about 6.9. So there we go, right? We've got our population mean and also our population standard deviation there. Okay, so we've got those things. That's just going back and using our calculator to do so. And again, just notation-wise, I'm using the notation for a population because we're making that assumption. Let's go ahead and just do a quick split stem plot. Again, it's going to look pretty ugly, but we'll go ahead and do it. The stems here, well, some of them have a stem of 1 and 2, but these guys would all have a stem of 0. So I guess our split stem plot would look like 0, 0, 1, 1, 2, 2. Remember that the way you do this is that the leaves that are 0 through 4 go in the first one, and leaves 5 through 9 go in the second one. So I guess you would say 0 and 4, and then an 8 there, and then a 2, and then a 0. Now, I would be very hesitant about naming a shape for that, but I suppose if you really had to, you would probably call it right skewed. I mean, if we really had to give a shape, right? Because if anything, it's sort of sitting like that, right, with these pieces here, and it's going down like that to the right. Okay. Now, let's go ahead and use that central limit theorem. So we want to use CLT to predict the sort of mean and standard deviation for sampling distribution n equals 2. So let's go back and take a look at what the central limit theorem tells us. So first thing that the central limit theorem tells us is that the mean of the sampling distribution should be the mean of the population. So what does that tell us here? Well, that tells us that mu with an x bar as the subscript is going to be the same as the mu that we calculated there, and it's going to be 8.8. Okay, let's go back and see what we can say about the standard deviation. In terms of standard deviation, it tells us that the standard deviation of the sampling distribution is the original standard deviation divided by the square root of the sample size. So let's go ahead and do that. That tells us here that mu x bar is supposed to be mu over root n. We know that mu is 6.9. We calculated that, so 6.9 divided by the size of the samples, and we're doing size 2. So we should divide by square root of 2. And if we do that on our calculator, 6.9 divided by square root 2, you should get that it comes out as about 4.9, which you will notice is a smaller value, again, because groups are supposed to have less deviation than individuals. Okay, so all we've done here is we've calculated some things about the population, and then we did some predictions based on the central limit theorem. Now we're going to go ahead and actually construct the sampling distribution. So I think we're going to do that on the next page. I'm just going to grab this population stuff here. I think we would like to bring that. I don't know if we'll be able to. No, let's just go ahead and give ourselves a new page real quick. So remember, our population here is just 0, 4, what else was there? 8, 12, and 20. Okay, so let's actually go ahead and do the sampling distribution. N equals 2. So what do we need to do? Well, we need to come up with every sample of size 2 from this population. But remember, way back when we gave that definition, we said that the sampling distribution is the collection of every average of every possible sample drawn from the population with replacement, meaning that the same individual can be chosen more than once. So let's go ahead and start thinking about what we're going to have here. First of all, let's think about how many we're going to need to write out. Well, how many choices do we have for the first person? Well, there's 5 individuals, so we're going to have 5 choices. Then we're going to have to choose the second person, but remember, we replace the people that we choose, so we're going to have 5 choices again. So there should be 25 samples here. Let's see if we can write them out. Well, they'd be things like 0 and 0. You could choose this person and then choose them again. You could have something like 0 and 4, or 0 and 8, 0 and 12, 0 and 20. Those would be all the samples where you chose the 0 person first and then somebody else the next time. Then you could have things like 4 and 0, 4 and 4, 4 and 8, 4 and 12, 4 and 20. I suppose you could also have things like 8 and 0, 8 and 4, 8 and 8, 8 and 12, 8 and 20. And you could have also things like 12 and 0, 12 and 4, 12 and 8, 12 and 12, 12 and 20. And then finally, you could have all the ones that start with 20. So 20 and 0, 20 and 4, 20 and 8, 20 and 12, and 20 and 20. So how many do we have here? Well, I put them in 10, 20, and 25 as predicted there. Okay, now, is that the sampling distribution? Well, no, that's all the samples of size 2. But the sampling distribution is the average of all of these. So I'm going to change colors a little bit and write the average of these. Now, I chose to do this with samples of size 2 so that the average is literally just adding these numbers together and dividing by 2. So the average here is going to be 0, and then 2, and then 4, 6, 10, 2, 4, 6, 8, 12. Then we should have 4, 6, 8, 10. That looks like 14, 6, 8, 10, 12, and 16. And then 10, 14, 10, 12, 14, 16, and 20. These green numbers, those are your actual sampling distribution. Those are all the averages of all the possible samples of size 2. Now, I hope that this is already convincing you guys that in the future, we want to avoid this. This is an incredibly small scale example. We only have a population of size 5, and we're only taking groups of 2, and it already took this much work to talk about every possible element of the sampling distribution. In the future, we'll skip all this and just use the central limit theorem. But again, I really just want to hammer home here that the sampling distribution is about the average of all the different samples. Okay, let's go ahead now and get the mean and standard deviation of sampling distribution. So let's take the sort of green data and pop it into L1 and then use our 1 var stats to actually see what we get there. So we'll go ahead, we'll type in all these averages here into our list and then use the 1 var stats there. If you do that, what you should find here is that the average of all those, which of course would be mu x bar in this case, if you type in those, you will get 8.8. Does that seem familiar? Yeah, it should, right? That if you go back over here, right, that's exactly what we predicted according to the central limit theorem. So in other words, the central limit theorem tells us it's 8.8, and if we go through and we manually take all these, put them into our calculator and get the average of all of them, we also get 8.8. So the first prediction is confirmed. If you take the standard deviation of all these, right, so again, you use your 1 var stat here, you will get 6.9. Or sorry, you will get 4.9. Does that look familiar? Well, if you go back over here Yep, that's exactly what the central limit theorem predicted. So again, could have just used the central limit theorem, but we wanted to do an example where we did it from scratch. So we calculated all these possible averages, the standard deviation of all those averages, 4.9, as predicted. So both the predictions came true. All right, we've got one last thing to do with this. What we'd like to do last is actually take a look at the shape of this. According to the central limit theorem, if we go back, the third and final component, right, we've sort of talked about this guy, we've talked about this guy, says that the sampling distribution should be more normal. Remember, in our case, the data was sort of right skewed. So we're expecting that it's going to be more normal than that right skew we initially saw. So let's go ahead and take a look at that. So let's go ahead and do a split stem plot here. Again, of just these sort of green data points. So we've got our 0, 0, 1, 1, 2, 2. Let's go ahead and see what we have here. In that first 0, we've got things like, looks like we've got 0, 0, and I'll just keep track. I use that guy. Then we've got some 2, so 2, 2, just looks like that's it. And then some 4s, 4, 4, 4, so 3 4s. There we go. Okay, then we'll have to think about the ones that go into the next 0, which would start with those 6s there. So let's see, we've got 1, 2, 3, 4 6s. So 1, 2, 3, 4 6s. Also, the 8s would go in there, and we've got 1, 2, 3 8s. So 1, 2, 3. The 10s would go into this guy. So it looks like we've got 1, 2, 3, 4 10s. So 1, 2, 3, 4. We've also got some 12s. So we've got 1, 2, 3 12s. 1, 2, 3. And then we've also got some 14s. Looks like we've got a 14 there and a 14 there. So 14 and 14. Okay. Now we're going to move into the 16s. So I guess we've got 1, 2 16s there and there. And then we also have a 20, right? So that guy would go right there. Okay, now what sort of shape do we have here? Well, I don't think we'd call it normal, but I think we certainly would probably call this more normal. You can start to see that there's sort of a peak rising here. We still have a lot more data over here than we do over here, but certainly this shape here, even for the sort of small samples of size 2, definitely looks more normal than we originally had. And remember, the central limit theorem says that it shouldn't really look normal until we take samples of size 30 or more, and we only did samples of size 2. But hopefully this justifies that last fact to you guys, that as you do these sampling distributions, things will become more and more normal. Okay, so that sort of ends the introduction to this sampling distribution. In the next couple of videos, we'll actually see how to perform computations using the sampling distribution, and we'll skip all of this stuff. And instead, we'll just focus on using that central limit theorem to immediately know things like the mean of the sampling distribution and the standard deviation of the sampling distribution.